Actually, I'm gonna give you about 10 minutes or so to try and find the kind of system for each of the molecules that are remaining in there.
What do you mean?
So, is it aromatic, non-aromatic, anti-aromatic? You guys have the rules? Give it a try on your own. 10 minutes, you guys can talk to each other. That's completely okay.
I still don't get how something can choose to be SP2 or SP2. Like that, and he tried explaining it with the orbitals that it.
Yeah, he was explaining with the orbitals.
They're like, it's like.
It's based on stability or just because? Just because. So, yeah. Other than that, like the actual explanation is what he did in lecture with the orbitals and all of that. But I know that confuses most students, so that's why I don't want to talk about it. I just say it chooses to be SP2 or SP3. So yeah. Hey, Lisa.
Actually, like I found that out.
Yes.
So this one is not constant, right? This one's not either, but this one is.
Both are fully
Okay.
carbocation and carbon.
Okay.
Yeah. Heteroatoms only contribute one of their lone pairs, correct?
Are they single bonded or double bonded?
Single bond.
Single bonded, yeah, it's gonna be two. If you guys have any questions, just raise your hand.
That is.
This part it doesn't. For the benzodiene with the radical, you only count one electron, just the radical.
Just for the radical, yeah.
So.
Radicals contribute one pi electron. In that case, yeah.
Which one we on? Just first try the one right after the next, this right here. Yeah. The benzodiene radical. Does a radical count towards conjugation?
Yes.
Yes. Physically, because it's in the p orbital. So as long as there's a electron in the p orbital, it helps towards conjugation.
Mm-hmm.
Holding that, right? That's two.
5 more minutes.
For this could choose to be SP2 or SP2. Yeah, if it's And there would be, but there would be 4 pilot. And make it entire. If it was SP3, it would be not. Can you do it? I don't like that I don't know why.
Hey, you think about it,
So like, because anti-aromatic is less stable than
oh, no, but I gotta think it's.
Yeah, I guess.
no. If it was SP2, it would be complicated.
Yeah.
But because.
Kind of relies on that.
On it, no matter what you want for lecture, aromatic is stronger than not aromatic, and is stronger than anti. So you're choosing between anti and non. So it's. Yeah.
I know, it's definitely.
We have a break within the conjugation unit, right? So my question is, with this, all still conjugated? And then
So
this
this
bar-
little guy is still conjugated. Remember the last example that we did over here? We said that anything that's sticking out, any carbons that are sticking out, technically they're gonna be acting like a carbocation. Carbocations, sp2, everything is fully conjugated. Same process over here. Everything's fully conjugated depending on what's the choice of the heteroatom.
So the only heteroatom that is bothering me is this one right here, because it's, so this has two pairs of lone pairs. One, two, one, two,
Mhm.
one, two, one, two.
Same thing.
So this is all conjugated, I understand, but when I get to here, you're saying that this acts as a carbocation.
Technically, it also has a carbocation. Plus also, if you remember from Orgo 1, sp2 is anything that has 3 amine groups, right?
Uh-huh.
So one of the groups is gonna be to the left, the carbon. To the right,
I
we have
thought
that
the con-
oxygen.
I thought the
They're
key to conjugation was pi electrons.
Pi electrons, and also everything has to be sp2. That's the basic definition of conjugation. That's
So
when
in
we
this
start
case-
talking about slowly
So
about
in
pi
this case,
electrons.
the carbon has a pi bond to the oxygen, so it's still technically conjugated.
Mhm.
Yeah.
Everything's conjugated.
I'll give you-
Kayla,
Triangle one. That one, because boron is always sp2,
Mhm.
so it's conjugated.
Yes.
All in the song.
All kind of digits are 2, 4, 6, 8. It's,
Wait, but it's not. Latest, right?
yeah. That means, carbocation, so if there's a positive charge on a carbon, there's a positive charge, it would also count towards conjugation.
Yes, but it doesn't contribute any pi electron.
So it's not.
Carbocations are gonna be sp2. We have 3 groups.
That's it, oh, okay.
So
I think.
this case, this is all conjugated.
Carbon, carbon. All of that part, but that one too. This carbon in here has 1, 2, 3 groups. 3
Still
groups,
sp2.
it's sp2.
There's no pi electrons.
There's no pi electrons in this case, but it's still sp2.
So
That's
pi
why we
electrons
start building
aren't
up.
necessary.
Not always. As long as you're sp2, you're good.
Hey, Stan, she said.
For no reason, 'cause I don't like carbon.
It's a Monday. Okay. So it's been 10 minutes, so did we solve most of them? Okay, 2 to 3 more minutes, okay. And then volunteers.
Non-aromatic. It's stuck in anything, no, it's stuck in anything. Because all the pylons are locked in. So it can't, not. No, remember how I folded it up like a little way? I don't understand what it is, but. Oh, you know why? After 8 5, just said it earlier.
Oh,
After 8 5, you choose to be player, non-player, because.
Yeah, okay.
Alright. Oh.
It's not even like for my school. I volunteered to.
You have 3 pylons, and then one from each header.
It's literally just changed. Like,
Because those
oh, yeah, it's like, yeah, like, it's Chrome. I don't think it's your root. No, it's gonna change with heat, like it's like.
Well, it's aromatic. Aromatic more stable than that.
Oh,
True.
true. But how do you think?
Like-
There's some goals on it.
I like that. Aromatic.
I see what you're saying, yep.
Yeah, I don't know. I have a little plastic.
Wait, where did you go? It's like 12 around. Oh, I'm sorry.
Magic, but it's that's what kind of, because if I magic, I literally, I'm interested in. Pretty shape, right? Yeah. I like, I like the S group of them. It's like a.
Wait, what's the other?
That's like, I like that one, and I was that I think.
Yeah, so it's 2, 4, 8, and then off you had a pair, so it's 2. So that makes it 10. There, that 10. Whereas this one, boron only has 3 electrons.
Okay, are we good to go over
Yeah.
the problems?
Yes.
Are we good?
Alright,
Okay, I
let's
need
go with-
5 volunteers. Okay, I have 2, 3,
All
so 4, 3. Choose your column, 1, 2, 3, or 5. Or 4.
oh, like column at a time?
Yes, that's why I only need 5 volunteers.
Wait, you said how much? No, it's 16. So 47.
No, like my big teal one that was the sticker.
First one, it is aromatic.
How did find it?
Oh, that's it.
6,
Oh,
aromatic. Non-aromatic. It's not fully conjugated. Non-aromatic. Okay, before we continue, double check those last 2 problems.
Sure.
Double check them. they're not gonna be non-aromatic.
Oh, they're anti. Cause they're stuck in that configuration.
They're gonna be anti-aromatic.
Okay, we got this. Wait, why is this one not non-aromatic?
8 pi electrons, does it follow Huckelfield or the anti
Okay,
rule?
but
It can't.
It
the,
has
um,
7
the lone
members.
the lone pair on top.
1, 2, 3, 4, 5, 6.
Or is it one of those cases
Seven,
where
eight.
it's there, so it's dealt with?
That one's just 8 pi electrons. We have
So it's
2
not
from
all
each
uh,
hetero.
level 1 and the carbon ion contributes 2. 2 pi electrons, which gives you the total of 8. 8 is part of the anti-rule. That's why it's gonna be anti-aromatic instead of non-aromatic. Okay, because that molecule is still gonna be planar. We just have 7 members in there. It can choose to be non-planar or planar if it has 8 or more members. Okay. And very last one.
Oh, so it's, no, what?
Double check.
Oh, non-aromatic, 'cause it can shut the egg.
Exactly. It can choose to be non-planar. There you go. Great job.
Example of the boron one, how is it anti-aromatic instead of not aromatic?
Because that carbon, it's stuck in that configuration. It's not like one of those heteroatoms where it could withdraw.
Remember the rules. Carbocations, carbon ions, radicals are all gonna be sp2. Okay,
Oh, okay, so it's gonna be plain.
do we get it? We got it. Okay, second volunteer. Okay, there we go. We have volunteer all the way in the back. Okay, you can choose your color. That would be good, yeah.
No, it's just.
You can change everything, the pen, the highlighter, whatever you want.
Whereas this one.
The bottom,
Yes.
because it can choose to be non-planar. Remember, rings with 8 or more carbons, they can choose.
So.
Good point. So in this case, we have 8 pi electrons, but I understand these two are lone pair. So you said that 8 pi electrons or more can switch their configuration.
If there's a heteroatom, correct? If it has eight or more pi electrons, it can switch from planar to non-planar.
No. The rule with the 8th number was if a ring has 8 or more members, it can choose to be planar or non-planar.
8 or more members.
Members. That includes carbons, oxygens, nitrogen, any of that.
So this is 7.
That one's 7, so it's gonna be
This is
planar.
7, not 8.
There you go.
Yeah.
So it's not pi electrons, it's.
The members. Exactly.
We're all here
So-
like
One can choose the thing.
surviving.
And that's just for rings, not like.
Just for rings.
Not used ring. or-
Just for rings, for one ring. Double check that molecule. They have to agree, yes. Single bond heteroatom, same hybridization. sp2, sp3. The oxygen sticking out from the, for that carbonyl portion is not going to contribute anything to the ring.
That. Oh, because we did it.
Oh.
Yeah. Oh, carbon. Yeah. Yeah, so every time. You can say that right there. It's like, it's set, it's set to, yeah.
No.
I got this actually. I got this. I'm a little friend, but it's not all, so. And, it's.
This one. Oh.
Is it cool?
Is it? Not the- which one? It's the top one. The- No, it's gonna. And- oh, my God.
Eight.
This in. So he built.
No.
That gives you 8 pi electrons.
Those.
Oh.
I love.
Which is anti. And then if it's sp3, non-aromatic. So what's gonna be the final answer? Non-aromatic, beautiful.
Would it be a methyl decaphenyl?
Great question.
What methyl?
That one, it's aromatic. And then the previous one, you said first one was non-aromatic, that's correct. Second one, non-aromatic, and then third one, it's aromatic. Beautiful, great job. Third volunteer, anyone?
Oh, the turkey.
Thank you, great job. Yeah, Lily, you wanna give it a try? Any calling that you want,
Okay, try call.
go for it, give it a try.
Lemon is. Decade. And then a dodec. And then trident.
All of those, so they're not quite that. You know, this question, no, this is the. The fountain of.
I wish.
It's fun stuff, bro.
Alright, 20 is.
You're doing good so far, you're doing good so far.
Iococine. And then 21 is. And iococine.
And the third number is a Y.
This is where.
Give it your best guess.
That's. I don't even know where.
How many pi electrons do you think it's gonna have?
Do I have to do the SB2? Because the nitrogens have to choose.
So the nitrogens, are they single bonded or double bonded? So they get choose, right? If they're sp3, it would be non-aromatic. If they're sp2, each of those nitrogens is gonna contribute 2 pi electrons. Can follow Puckle's rule or the NT rule? Puckle, so is it gonna prefer to be? Beautiful, great job, Kayla. You got it.
How that's really conjugated.
Yes.
Because I thought you like excluded the bond. Oh, what is it?
This part,
Yeah, but I see it now, I feel like.
everything has sp2, exactly.
I'm used to like just looking at double bond and now I like.
Volunteer?
I like the.
Guys, lower your voices a little bit for now. Yes. So yeah, in this case, each nitrogen is gonna give you 2 pi electrons because they're single bonded. That was the rule. Okay, 2 more volunteers. Okay. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Each of them gives 2.
Yeah.
So that's a total of,
Does.
no, they're like carbocation. So they don't give you any.
The type of, if I had the.
Yeah, I understand.
Aromatic, perfect. Perfect, it is aromatic.
That meant that I.
I.
Diagnosed.
I used to for that. I can't do it right now, but I do it.
Aromatic, beautiful.
Yeah, I got it.
Very last one.
The trumpet is like a derivative.
I graduated.
And it chooses to be aromatic, beautiful. Great job, you got it.
The other day I told someone
Great job.
about.
Okay, last volunteer
Compound.
for the last column. It's just 3 molecules. Vicky, do you want to do it? Go for it.
That was me the other day. I told someone about. They were really.
The planar or non-planar thing.
And I. Not like.
Eight or more.
Yeah.
I have actually last person take off. Lost my patience.
How about you do like, computer degrees? Yeah, I was thinking of. I'll go and stay. Yeah,
So
This wasn't part of the last
you're doing good. The carbonyl group that's sticking out, remember, it doesn't contribute anything to the ring. So it's gonna be like a little carbocation. It's gonna be sp2, but it's not gonna give you any pyralex.
Person, I'm thinking that.
It's funny how.
But if you
this
just.
is-
Mhm.
You can recall that these chemicals shouldn't go together.
burn out.
I mean, these are the type of things that you go in.
So it's gonna be here.
That's why you can't do that.
Very last.
It's not remembering all this. Yeah.
It's like a sliding door. Yeah.
Yeah. So you go look at that thing, right? On the,
Perfect, great job, Vicky. You got it.
the amount of resources that's question. I was confused. I was like,
Okay, everyone, did we all get the same answers? Y'all got them? We're good? Does anyone need me to re-explain anything?
Or just double bonded, like for the oxygen or the carbonyl groups, what are they counted? They're just disturbing when it comes to determining if something's conjugated or not.
So carbons, remember, as soon as you see double bonds, they're always gonna be sp2.
Okay.
So that's a good way to tell it. And also if you check the groups, Same process like we saw in here. It has only 3 groups, which makes it sp2.
So it remains conjugated because those are sp.
Mm-hmm, exactly. You got it. Okay, any other questions so far? Yes. The third one and which one? Oh, wait to the right? This guy. So this guy is non-aromatic because it's not fully conjugated. That carbon at the very top, it's sp3. So as soon as we break one of the rules, non-aromatic. Okay. Yes. Mhm. So whenever you have a heteroatom that can choose to be sp2 or sp3, it's going to be based on the stability of the molecule. So if it's sp3, for example, it's going to break the fully conjugated rule, which makes it non-aromatic. But if it chooses to be sp2, depending on how many pi electrons you have, it can be either anti or aromatic. If it's non-aromatic versus aromatic, you're going to choose to be sp2, so the molecule can be aromatic. Okay, any other questions? We're good? How do we feel so far about chapter 14? Do we feel good? We're good? For being we want to stop right there, but no, not today. And actually, if we have time, we might start 15. So we'll see.
Full hour to work day. That's all.
Yes. Okay. So let's go back to this little theory. Okay, we're familiar with it. We know that we see that with any conjugated system, but so far we learned them for linear conjugated systems. Now, whenever you have anything cyclic, it's gonna look a little bit different. Okay, but the concepts are gonna remain the same. Now, first thing that you should know is that whenever you're trying to find the energy diagrams, each of the orbitals and their places, the array, it always has to be in a certain conformation, in where at least one carbon it's at the very bottom, only one, and one carbon is at the very top. Okay, we just need one lonely carbon on each side, top and bottom. So that's why this guy is also drawn like this. Okay, that's why. Now,
Oh, I see, yeah, okay, that's what you're saying.
okay, so at this point, we should know how many sp2 carbons we have in that case. How many do we see? 6, which means that I have.
Aromatic.
What are you talking
Well, yeah, it is
about?
aromatic. What does it tell you about the theory? If I have,
2 and 1.
What do you think?
Like all the p orbitals equal.
so, yeah, you have 6 carbons that are sp2, but remember, the number of sp2 carbons correlates to the number of orbitals that you're gonna see. Okay, so that's why we have up to pi 6. Okay, so far we're good. We know how we got to that place. Okay, now, how many pi electrons do we see in total? 6. Okay, 6 pi electrons. And remember, we always fill them from the bottom to the top, so pi 1 is gonna have 1, 2, pi 2 has 3 and 4, and pi 3 has 5 and 6. And now, really quickly, what was HOMO? Highest occupied, so that's why pi 3 is gonna be HOMO, and then LUMO, what's the definition? Lowest unoccupied?
And then it's gonna jump up, we're gonna have 1 electron at the equal.
Exactly. So before I draw it out, how many pi electrons am I gonna see in the HOMO orbital in the excited state?
1.
1. But remember, all of your questions are gonna be just basically word problems, and that's it. Okay, he's not gonna be drawing the energy diagrams and all of that. So I have 1, 2. Okay. So far, questions on the benzene group. We good? We're good. We see it. Okay, now, in this case, let's quickly remember what I said about an even number of orbitals. So whenever we have an even number of orbitals for linear conjugated systems, we said that we're gonna have the same amount of anti-bonding and bonding and no non-bonding orbitals at all, right? Okay, now, it's gonna somewhat apply the same to this. Now, in this case, after you get your molecule in that conformation where you only have 1 carbon at the top, 1 carbon at the bottom, that's where you're gonna start drawing out the orbitals. Now, in this case, you're always gonna split it in half. So that means that I'm gonna cut it right here in half. okay, horizontally. I have 3 up and 3 down orbitals, okay? So I have an even split in that case. Now, it's gonna get a little bit more tricky when we get to this guy, cyclobutadiene. In this case, we have an even number of orbitals because we have 4 sp2 carbons. How many pi electrons do we see? 4. Now, again, we always start from the bottom to the top, so 1, 2, and then, oops, this is supposed to be 3, and this guy was supposed to be 2. Yes,
Okay.
yeah, that was a typo on my end. You can switch them.
No, I'm saying like isn't it like one electron in HOMO and then one in the other one?
That's for the excited state. Right now, we're in the ground state. We're drawing out the ground state.
Okay.
Okay, now, in this case, we have an even number, but remember, the rule for cyclic structures is that you have to split it right in the middle horizontally. So in this case, if we do that, we're gonna be going through 2 orbitals. Now, whatever we go through in that line, those guys are gonna be your non-bonding orbitals in this case, okay? This only applies for cyclic structures. Remember that if you're looking at something that's linear, an odd number of orbitals means that you have an odd number of sp2 carbons. Yeah, backwards, but yeah.
So what if you have an odd number of carbons?
He's not gonna be asking about that. He only asks about benzene and cyclobutadiene. Questions so far? We're good? Do we see it? Can we kind of see it?
Who would split that electron? Like one electron in HOMO, one in 5-3. You know what I'm saying?
You're saying like one electron in pi 3, electron pi 2.
That's like that.
Isn't that the
Yeah.
excited
Like
state?
this.
Oh, is that
And
the
why is the excited state jumping from P2 to P4? You have the LUMO on P4.
Okay, let's take it back. Let me erase that. Now, in this case, whenever you're talking about cyclic structures, the exact order of pi 2 and pi 3 in this case is not gonna matter. They can interconvert each other, okay? Because at the end, they're in the same energy level. Now, we know from general chemistry that we have to feel each of those orbitals, right? Before we complete them. Now, in this case, same process for HOMO. We know that HOMO is the highest in energy that's at least occupied. Technically, because we know that pi 2 and pi 3 can interconnect each other, they are both going to be HOMO. So in this case, that whole energy level is going to be HOMO. So let's just add it in here.
But isn't that configuration just because we had a cycle of the dying and like the carbon on top configuration? What if it just tilts the 90 degrees to the right? Then you have P1 next to P2 next to, no, go down. So like if you were to just take this right here. You just twist it. This way.
Now you have P1 and P2 with P3 and P4.
Yeah, but that's not how we draw the orbitals for cyclic structures. That's why I told you specifically. For cyclic structures, it has to be in that specific conformation, let's say. One carbon has to be sticking at the bottom, one carbon has to be sticking at the top. Now, in the excited state, we know that we're just going to jump one of those pi electrons in HOMO to the LUMO orbital. So I still have 1 and 2 in pi 1. And now, in this case, it's not really going to matter from which orbital you choose to jump it from, but we know that at the end, we only have 1 electron in the HOMO orbitals and 1 electron in the LUMO. Okay, so far, questions? It's slightly different.
So the cyclic structure, you can have 2 LUMOs.
Yes.
You have 2 LUMOs.
No, we're just gonna have 1 LUMO. It's based on the energy level. Based on the energy level.
You're gonna post these today?
Yes. Okay, questions on this theory for cyclic structures? We're good, we got it. And again, same process. He's gonna be asking just word questions with this. He's gonna give you the name of the molecule. He's gonna ask for the number of pi electrons in either the ground or excited state. So that's practically it for chapter 14. So Now that we know everything, how are we feeling about it? Yes, I'll see you Wednesday. Now, do you guys want to start to talk about chapter 15? Really briefly? Please no. Slightly? Okay, slightly, that's me. A soft introduction, okay.
I gotta go.
Play 2, okay, play 3. Okay. We don't wanna, okay, I'm only gonna show you the little spider web for those of you who want to stay. Now, chapter 15 is gonna be a lot easier. It's gonna be 5 reactions that you have to know, which are just in there, the spider web in there. The only thing that you have to remember is the reagents and what's the final product. We're just gonna be adding a little baby piece of the reagent into the benzene group at the very end. The reactions in this chapter, they're all gonna happen with benzene group, okay? Now, so it's gonna be a lot easier. Now, whenever we talked about electron withdrawing and electron donating groups, in this chapter, we're gonna call them something a little different. Activators and deactivators, but we're gonna talk more about that on Wednesday, so I'll see you guys Wednesday. So that's it, just cute little introduction, yes. I mean, yeah, you can do a bunch of reactions with a benzene group, but those are the 5 main ones for this chapter. So yeah, I wouldn't worry too much about it.
Thank you very much.
No problems. See you Wednesday, guys.